Okay, this is number 3 for the practice exam. It's dealing with system properties. It gives us a function y of n equals x of minus n plus 3. The first system property we need to check is if the system is memoryless. So the easiest way to do this is going to be finding a counterexample. This is a pretty easy one. You can just kind of test values and see if we put, say, y of 2 is equal to x of minus 2 plus 3. Okay, so our current input was t equals 2, and our output y of 2 is depending on a past input x of minus 2, so clearly this system has memory. So if you say found it to be memoryless, in this example you wouldn't, but maybe check two values if you find that it is memoryless, because there are some systems where you may not find a counterexample with the first value you test. Okay, so the second part is asking us to find if it's time invariant. Okay, so the condition for time invariance is going to be that if we shift the input first and then put it into the system, we get some output that would be equal to if we put the input into the system and then shifted it. Those two should be equal if it's a time invariant system. So practically what that looks like is we'll take an input x of 1 and we're going to send it into the system, and just by definition the system spits out y of n equals x of minus n plus 3. Okay, now we're going to send that into a time delay equal to n naught, and we get the final shifted output of y n minus n naught equal to x minus n naught plus 3. Okay, so now let's try it the other way. Let's first shift the input and then feed it into the system. So it's the same time delay equal to n naught, and we get x of 1 n minus n naught. Now we're going to put it into the system, and that's going to be equal to x1, just to be clear, that is still x1 up there, x1 minus n plus n naught plus 3. Okay, so these are not the same. they're not the same. So this system is not time invariant. Okay, so part C asks us to find whether the system is linear, and the system is of course given again by yn equals x minus n plus 3. Okay, a system is linear if it obeys the principle of superposition, and hopefully you know what that is. If you don't, go look up the exact definition on the midterm review, because I'm not going to give it here. I'm just going to test. First, we're going to put the principle of superposition as two parts. It has to obey the principle of additivity, and it has to obey the principle of scaling. So first we're going to do additivity, and if it's false, we won't have to check whether or not it obeys the principle of scaling too, and that will be nice. So the principle of additivity says that if we take two inputs, x1 and x2, add them, and then send that into our system, we should get the same as if we sent each input into the system individually and then added them. If that's true, it obeys the law of additivity. Okay, so from here we're going to get just x1 minus n plus x2 minus n plus 3, and it's just plus 3, 1 plus 3, because just one single plus 3, because we're adding to 3 to the input signal, in which case the input signal was the summation of those two. Okay, so let's check the other way. We are going to send each one into the system individually. And we get x1 minus n plus 3. Okay, x2 we're going to send into the system, and we get x2 minus n plus 3, and this is just the behavior of the system. Of course, we defined it right here. Okay, so if the law of additivity, sorry, I keep saying principle, but it's law of additivity, if it's true in this case, when we add these, we should get this. But you probably can already see that we're not going to get that. Get x1 minus n plus x2 minus n plus 6. And these are not the same. So this system is not linear. And had the law of additivity given us affirmation, in a different scenario, we would have had to check the law of scaling too, to see if that is true or false, and if it was true, then the system would be linear, and if it was false, the system would not be linear, because both conditions have to be true under the principle of superposition for it to be linear. Okay, the part D asks us to find whether the system is causal. And a causal system is going to be one that depends only on present or past inputs. So like part A, we can just do this by kind of guessing, putting in values and seeing what we get. So if we put in y of minus 2, we get x of 2 plus 3. In this case, our present input was x of minus 2, because we're at t equals minus 2. This is kind of weird to think about being at negative time, but remember, this is discrete time, so, and also we could be on a computer, so we're not actually in negative time, but we are, so don't get too hung up on that. But we can clearly see that our current input is x of minus 2 at t minus 2, and our output y of minus 2 depends on a future input, x of 2. So this is not causal. Okay. E asks us to determine if the system is stable. And our condition for stability says that if x of n, our input, is bounded by some upper limit b, then our output y of n also needs to be bounded. And we're going to write that like this. So definitely then we can see that this is bounded, where the upper limit is b plus 3. So since x of n is bounded, then so is y of n, and it's stable. Okay, that's it for problem 3.